All right, we are going to be graphing radical functions today. So this is section 5.7, obviously. And our joke of the day, how can you predict how many protesters will show up at a rally? And you might guess it has something to do with radical by using a radical function, which we're going to be working with. So we're going to be working with radical functions and square root functions. Radical functions are anything with a radical in it. And a square root function is more specific because it has a square root, which is a type of radical. And then here I've got that we want to discuss inverses of quadratics and cubics. So if I draw a quadratic, that's a squared. Let's do the parent function, which would be f of x equals x squared. And we know it passes through 0, 0, 1, 1, here 2, 4, negative 2, 4. And there's our quadratic parent function, f of x. And you may or may not remember that in order for a function to have an inverse, it has to pass the horizontal line test, which is the 1-to-1. It has to be 1-to-1. And if I draw a horizontal line, I've got a problem here because it crosses more than once. So that means that f of x equals x squared, the inverse of that will not be a function. But what we're going to do is we're going to force it to have an inverse because we want it to have an inverse. And so what I'm going to do is what we do as mathematicians is we're going to just take part of the parabola. And if I just choose this yellow highlighted region, does it pass the horizontal line test? And yes, it would, because it would only cross once right here, since this part isn't part of it. So then what we do is we find the inverse of that portion of it. And if you remember, still on highlighter. Remember y equals x or y equals eggs? That one little joke we had. If I reflect this yellow curve over this dashed line, I end up getting this curve right here. And that is the square root of x. So that would be, actually let's do it. Let's write it correctly. That'd be f inverse of x equals the square root of x. So inverses undo each other. If we have something squared and we want to undo it, we take the square root. So hopefully that all makes sense. And then we'll talk about domain and range on the next one. This is right now I'm just kind of talking about an intro, so you don't have to write this down because we're going to be looking at these a little more specifically later. And then cubics are the same idea. Let's graph the parent function x cubed. And I'm just going to graph it quickly because we've done these before. It passes through 0, 0, 1, 1, 2, 8. So way up here. Negative 1, negative 1, negative 2, negative 8 way down there. So there's x to the third. Does this one pass the horizontal line test? Yes, it does. If I draw a horizontal line, it's only ever going to cross it at one point. So that means I can simply draw the inverse of this without any worries. And when you reflect it over the line y equals x, you end up getting a curve. Well, these go down here. Whoops, I think I went, yeah. No, it should go. Yeah, I did that wrong. I knew that didn't look right. This reflects to here, and this reflects to here. It goes like this. Whoops, I kind of missed. I should have done it in a different color. We'll go over it with blue. So that is the cube root function. Cube root undoes cube. That was the main idea I wanted you guys to get out of this. Okay, we already talked about this. A radical function is a function that has a radical in it. Square root function is that's the parent graph for a square root function, the square root of x. Now we're going to graph the square root of x again. I just graphed it in the introduction there, but this time we're going to be a little more careful about it and we're going to pick some points. So if I did negative 2 here for my x and I wanted to take the square root of negative 2, I would get an imaginary number, right? I'd have to write that in terms of I. But I only want to graph real numbers. So I don't want to use negative 2 because I get a non-real answer. So the first number that I can plug in there that's an integer is 0. The square root of 0 is 0. Can I take the square root of 1? Yes, the square root of 1 is 1. What's the next number I can do in my head that I can take the square root of in my head? Well, that's going to be the square root of 4, which is 2. And then the next number I can do in my head would be 9. The square root of 9 is 3, and so on. So we're being very selective about the points that we pick for our x's so that we can do this in our head without a calculator. Oh, and I need to go all the way out to 9, don't I? 1, 2, 3, 4, 5, 6, 7, 8, almost 9. And then I have the point, sorry, 0, 0, 1, 1, and 4, 2, and 9, 3. And it's just, it has the same shape as a parabola kind of flipped on its side. So that's the square root of x. When I'm graphing these, I usually just use these 3 points here. I don't usually go clear out to 9. And then let's talk about the domain and the range. So the domain are the x's start here at 0, and they are inclusive. It does include the 0, so we need a square bracket. And we go all the way out to infinity on our x's. Our range are our y's. The first y we encounter is also 0. And it also goes up, 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 up forever. So the domain and range are identical on this one. Now we'll do the cube root. And I already did this briefly on the first slide. So again, this time I want to be selective with my x's. I want to choose numbers I can take the cube root of. Can I take the cube root of a negative number? And the answer is yes. So you want to think of some cubes, and of course what comes to mind is negative 8. Because I can take the cube root of negative 8. We just did that in the last section. It's negative 2. I can also take the cube root of negative 1, which is negative 1. The cube root of 0 is 0. And then 1, 1, and 8, 2. All the other numbers between negative 1 and 8 are ones I can't take the cube root of in my head. 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, negative 8. And we only have to really go up to 1 and 2, don't we? So the point negative 8, negative 2, negative 1, 0, 0, 1, 1, and 8, 2. And this is just y equals x cubed flipped on its side. Is the cube root. So that's what it looks like. And then let's do the domain and the range. Okay, domain are the x's. They go that way forever, so that's negative infinity. And they go to the right forever, which is positive infinity. The ranges are the y's. It's going to keep going down, 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 down forever in the negative direction. And as you go up to the right, it's going to also go up, 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 up forever. So again, on this one, the domain and range are identical, but they are all reals. Now we are going to graph, and we're going to use transformations because we are very familiar with those. So this is, what's the parent graph? Well, you see the radical, you see a cube root. So g of x is the parent graph. That's the cube root of x. The 4 out front, we know that that's going to be a vertical stretch by 4 from our previous experience. And the plus 4 inside the radical is going to move it left to right. It's going to go backwards. It's going to go left 4 units. So I could graph that pretty quickly by hand. Cube root. Let's see. I'm trying to go as fast as I can here. 1, 2, 3, 4, 5, 6, 7, 8, 8, 2. Because it's a cube root. 1, 2, 3, 4, 5, 6, 7, 8. Back 8 down 2. Okay, there's the parent, g. And then I have to stretch it vertically by 4. Sorry. So that means this point here, its y value is 1. I have to multiply its y value by 4. 1, 2, 3, 4. Whoops. So right here. And like this will stay 0, 0, and this one will go down to negative 4. So it's this, and then it's going to just go way down here. I'm not going to bother with the other ones. We have the basic idea here. So that's a stretch of 4, and then we have to move it left 4 units. 1, 2, 3, 4. Oh, it didn't change color, did it? This one's going to go right there. This one's going to go left 4, 1, 2, 3, 4. So essentially, it looks like that. This is your final function f. So that's how you would graph it by hand. Of course, we will go to the calculator as well, so that you can see, and this will verify. Y equals, we're going to just type in the one we're trying to graph, 4. I like to do, instead of the cube root, I like to raise all that to the 1/3. So I'm going to do parenthesis, x plus 4, close my parenthesis, raise 2, and I need my 1/3 in parenthesis as well. If you don't put the 1/3 in parenthesis, you're going to have problems. The other way you can do this is you can use the math button and do the cube root. So here, I'll go back and do that. So we'll do 4, and then math 4 for cube root of x plus 4. So both of those are going to be identical. If I go to my table, you'll see you have the same values. Now let's do zoom 6 and make a graph. And there it is. And does it look like the one we did? The pink one? Yes. Great. Oh wait, did I do domain and range? Domain and range. Domain, the pink one, it's going to be all reals. Range, same thing. Letter A, we already did that. We don't have to do that one again. Say, this next one, this is the square root function, so you have to look carefully and make sure you get your parent. So to do the square root, I'm just going to graph the square root of x first, and hopefully you're okay with doing this without a t-chart. Square root of 0 is 0, the square root of 1 is 1, and then I'm going to skip to 4, 1, 2, 3, 4, because the square root of 4 is 2. So there's my parent. And how's it being moved? The plus 1 inside is going to move it left 1. All these points are going to go left 1 unit, and there, oh, that's f. That's f of x. Now the domain are the x's, so notice it got shifted left, so my domain, my x's are now going to start at -1 to infinity. My range, it doesn't change because it didn't shift up or down, so it's still from 0 to infinity. Okay, this table you are very familiar with, except for, of course, we haven't had it in terms of radicals before. So I don't even think I need to go through and talk about it because it's identical. These are all identical to what we've done in the past. So if you want, you can pause and you can copy this down, or at the least maybe pause and look through it. Remember, these are the tricky ones. Inside the horizontal stretches, you have to do the reciprocal, so a 1/5 is actually a stretch by 5. This is actually a horizontal compression by 1/3. Remember, the negative out front reflects it vertically, which is across the x-axis. And this, because it's inside with the x, you can think of it as a horizontal reflection, which would be across the y-axis. So, transforming these, you know, this is the same stuff I've been doing really on all these slides. I would say try these on your own, and then take a look, and I'll do these as well as fairly quickly. So the square root of x, if you do enough of these by hand, you're going to get fast at graphing them. And then -2 is going to move it down 2 because it's outside. So these get moved down 2, and we have that is g. The domain, oh, we don't have to describe the domain. Describe the transformation, and we graphed it. I already graphed it. The transformation is that it goes down 2 units. Okay, what's the transformation on this next one? It's a vertical stretch, right? By 3. So we'll graph the usual points here for a radical, noticing that the parent function is a radical. There's the parent, root x, and then I have to do a vertical stretch by 3, so I need to multiply every y value by 3. This y value, 0 times 3 is still 0. The y value is 1. I'm going to multiply that by 3 and get 3. This one, the y value is 2. 2 times 3 is 6. So way up here somewhere. So this is 3 root x. And we can confirm that on the calculator really quickly. This is a long section, especially when I find all these, whatchamacallits, these graphs. Okay. Kind of hard to see. But you could trace, if I do 4, I could do trace. I could type in 4 and see that it's 6, which is what I had said it was. So that confirms that we did it correctly. Okay, do these on your own, and then I'll tell you the answers. So this one's going to be up 1 unit. Do these as fast as I can. So there's the original, the parent, and then if it's going up 1, it'll look like that. This one is a vertical compression by 1/2. So the original, it's a root again, it's a square root again, so it's there. There's my parent. And now I'm going to be multiplying these y values by 1/2. So there's the final one. Okay, now we're getting into the heavy-duty stuff here. This is the serious stuff here. Please write this page down. If you haven't written down anything, at the very least, pause the slide, the video, write this down. Write this down. Super important. This is in a little different form than we've seen in the past. In the past, we haven't had these parentheses. Okay, what this does with these parentheses, what this does is it means that if you have a horizontal change in here, a stretch or a compression, that's going to happen first. Then the graph will get shifted. So when there's parentheses in here, this is the order right here of these transformations. And really the rest of the stuff inside is all the stuff we've seen before. It's just the parentheses are new. And in my opinion, we should have had them all along, because in the last section it was really confusing. Of course, I kind of tried to avoid those, but if there's parentheses, this is the order. If there's not parentheses, then actually it gets shifted left and right first, and then the horizontal stretch and compression are applied. Anyway, I'll just leave it at this, copy, and we'll move on. And remember this statement here that I wrote down. Okay, they're being nice to us on this first one. We don't have to worry about a horizontal stretch or compression. So it's still very straightforward. It's really the same type of problem we've been doing all along here today. So it's still a vertical stretch by 2, and it's just a straightforward left 3. And it's another radical. I'm wondering if I should even take your time to show you what it looks like. I guess I can do it as quickly as I can here. So here's the radical again. See how fast we're getting at those? And it's stretched by 2, so we need to multiply this by 2 and this by 2. All these y's by 2. Okay, there's the stretch. I'll call that h of x for the intermediate one. And then I'm going to be moving it left 3. So this whole thing gets moved left 3. And that's like back here somewhere. So here's g of x, the final one. I described the transformation and I wrote the graph, and then if you want, you can check it on a calculator. Okay, this one's a little more interesting. We haven't had a reflection yet today. The negative is inside the radical. It's with the x, so that's a horizontal reflection, which means if we're reflecting horizontally, we're going over the y-axis. Reflect over the y-axis. Whoops. Going so fast I'm making sloppy mistakes. And then it's also, since the minus 2 is outside, it's down 2. So, 1, 2, and it's still a radical, square root. When I say a radical, I just am meaning that's just a square root. Okay, here's my radical that we've gotten very familiar with graphing. That's g in this case. Oh, no, it's not g. Sorry, that's the parent. I don't know what I was thinking. And then we're going to reflect it over the x, the y. So that's going to go here, here, back 4 up 2. Okay, there's the reflection. And then it's going to go down 2. Go to blue. All the points are going to move down 2. Whoops, kind of missed, but you get the idea. And it doesn't ask for domain and range, so we are done with that one. I recommend graphing these on the calculator to check them. Okay, do these on your own. This one is another reflection over the y-axis because it's horizontal. It's going to go up 3. Getting real fast at those, so 1, 2, 3, reflect across the y, and move it up 3. 1, 2, 3. Now I'm just kind of save your time. It basically looks like that. So this is G. Why don't we graph one of these just real quick just to make sure everything's looking good. So I've got the square root of backspace, negative x, close the parenthesis, plus 3, graph. And then this graph is my final graph here. Okay, this one is outside, the negative's outside, so that's a reflection over the x-axis. The 3 is a vertical stretch. And the -1 outside is down 1. Tell you what, I'm going to just let you graph that on your own and check your graph on the calculator. Okay, example 4. This one is going to be the interesting one because it's going to be stretched horizontally. Anytime we're working horizontally, we're working with the weird stuff, the stuff that's backwards. And it's by a factor of 2. And then it's going to get reflected, and then it's going to get translated. So what I want to do is, I'm going to pull up that equation that I had you copy down. And I'll write it down exactly how we had it copied there. So we had f of x equals a, and it's the square root, 1 over b, x minus h, plus k is outside. So remember on this one, the order is, when it's written in this form, we do our horizontal stretch and compression first, followed by the left and right shift, which is exactly how this problem has been written. We're stretching horizontally first, and then we're translating back and forth. So this is the equation we're going to use because it's set up perfectly. Now we can just go through. Our parent function is a square root, so the square root will stay. It's stretched horizontally, so that's inside right here. Since it's a stretch of 2, it's actually going to be multiplied by the reciprocal, 1/2. So there we've got that. It's reflected across the y-axis, so that's that's horizontal. That's like a horizontal reflection, so that means the negative needs to go in here with the, in here horizontally. So there's no A out there. I'll call this G. And it's translated 3 units left. So the back and forth shift is inside with the X, and it's in the opposite direction. We need parentheses. So that's new. We haven't really had that before. So if it's left, it's actually positive because it's backwards from what you would think. And it's not moving up or down, so we don't have to worry about a K. Now this is something you definitely should graph because this is more confusing. Here, go away thing. This one, what is going on with this thing? There we go. What? All right, there we go. Y equals clear. Okay. Now to graph this, to key it in, second square root. Just to make it easier, I'm going to do negative 0.5 here so that I don't have to worry about parentheses. Now I need this parenthesis, it's very important. X plus 3, close. And if you want, you can close the parenthesis again around from here. Let's take a look at the graph. All right, there it is. So let's see. It was supposed to be stretched horizontally, first of all. And you can see that it does look skinnier. Here, let me go back and go down to y2 and put in the square root of x so we can compare the shape. Yeah, see how square root of x is a little taller, and this one on the left has been pulled horizontally, like kind of like stretching taffy. It pulled it out thin. So it's definitely a horizontal stretch. It reflected across the y, obviously, and then it got translated 3 units left, also pretty obvious. Let me show you what would have happened if you had not, call this h of x, if you had not used the parentheses and just had written negative 1/2 x plus 3. Kind of like this is what we've been used to doing. So second square root. I'm going to go negative 0.5x again, plus 3. Graph. Ooh, completely different. It did get stretched. It's skinny. But it did not move left 3, did it? It actually moved to the right 6. It did get reflected. It got reflected and it got stretched, but it moved a different way. So this is not equal to this one. This one you stretch then shift. This one you shifted you shifted left 3 and then got stretched. So that's not the way to do it for this problem. Okay, do this one on your own. This one's easier, and I'll give the answer. I think I'll just go ahead and, okay, so the answer is, it's reflected across the x, that's outside. It's stretched vertically, so that's outside. It's translated up, so that's outside. See, vertical is so easy. So that one is done. That was a cinch. Okay, this problem actually is as big as it looks. It's actually not that bad. Special airbags are used to protect scientific equipment when a rover lands on the surface of Mars. On Earth, this is the function that approximates an object's downward velocity in feet per second as the object hits the ground after bouncing x feet in height. So this is the height that it bounces, and this is the velocity, how fast, the rate of speed. Rate or speed. The corresponding function for Mars is compressed vertically by a factor of about 3/5. Write this function g for Mars. So let's do that first. So all we're doing is compressing this one vertically. Oh, that's so easy. Vertical is easy. It's just out in front, 3/5. Just make sure your x is under the radical. Done. First part done. Now use it to estimate how fast a rover will hit Mars' surface after a bounce of 45 feet in height. The 45 feet is the x, so we're putting 45 in here for x. So g of 45, because that's going in for x, is 3/5 times the square root of 64 times 45. And I suppose you could try simplifying that, but we want a decimal answer anyway. I'm just going to type it in. So I've got 3/5, that's 0.6, just to save time, times the square root of 64 times 45. Well, I already know the square root of 45, whatever. Anyway, 64 is 8, but times 45. I get 32.2, essentially. 32.2. We need units here. It is a velocity, right? How fast it's going, and it's measured in feet per second. So that's not too bad. Try this one on your own. You're still transforming Earth again. So for Earth, the velocity was, what was it again? I have to find it again. Or I could have went back a slide, I suppose. What was it? Square root of 64x. So this time, so do this on your own, and I'm going to be telling you the answer. It's a horizontal stretch by a factor of 25/4. So the horizontal is inside. V is for velocity. And that means I need to multiply by the reciprocal of 25/4. Since it's a horizontal one, it's backwards from what we would expect. And we get this. Now I'm noticing that I can take the square root of 4 and 25 and 64. So I could actually simplify all these. This is like saying the square root of 4 times over the square root of 25 times the square root of 64 times the square root of x is essentially what this is saying. So that's 2 times 8, which is 16, root x over 5. That's the new function. I'll call it v of x. Now, we are going to put in, what is it? It does say, okay, it bounces 50 feet. So that's our x. So we're going to plug 50 in here and see what we get. 16 times the square root of 50. Hit enter, then divided by 5, enter, 22.6. And we knew that was feet per second, right? So that's your velocity on Mars, or the moon, I mean, rather. Oh my gosh, there's more. I'm trying to go as fast as I can. These, though, are not bad. Really not bad. Graphing inequalities, we've done these before. What you're going to do is you're simply going to graph y equals the square root of x plus 2. And we've been graphing those all day here. So I'm going to be graphing the square root of x. Good old familiar points there. It's being raised 2 units. Whoops, that doesn't seem right. No, that should be right here. X that out, and then this one will go up here. Okay, so there's the y. And then, remember the less than is dashed, so actually you want to go back, and I'll do it with the highlighter. You need to dash that line in, that curve in. And then, I still have my highlighter here, which is good because I need to shade. So the extra 2 things you have to do is you have to figure out if it's a dashed or solid line based on the symbol. If there's no equal to, that means it's dashed, and if it was an equal to here, you would make it solid. And then we're graphing all the y values that are less than this curve. So the y's are, if they're less than, they're underneath. So all of everything underneath this curve. Notice I'm stopping at the y-axis. That's because the function's not defined over here. So don't shade parts of it where it's undefined. And this is our last slide. So you get to do these on your own, and then I will be drawing the answers here. Okay, this is the square root of x again. This time it's being moved to the left 4. And again, it's dashed. So another thing you could do is I could do little eraser marks and kind of erase these. It's dashed because of the greater than symbol without an equal to. And then I'm shading all the y's that are greater than, so I want everything above that. Oh, I hit the eraser, not the highlighter. And I had to be careful because, oh, yeah, there it is. It stops at x equals -4. We can't go to the left of there because it's not defined. And then the last one, this is the cube root. So I know that I'm going to graph the parent. It looks like this. It's kind of a quick sketch of the parent. And that one's -3, so that's to the right 3. 1, 2, 3. Oops, I'm going so fast I'm making small little stupid mistakes. Okay, this one is solid because it's equal to. So this is my solid line. And I want all the y's that are greater than or equal to. That's everything. Let's make this big. That's everything above this curve. And because the domain is all reals, it goes forever everywhere. So that's what you should have gotten for that one. And we are now done graphing radicals.